Hey, so what we're going to do in this video is we're going to go over what internal resistance is because we want to tackle this exam question. We're going to do a quick mind map on what internal resistance actually is. But remember, if you haven't seen the electricity part 1 video, be sure to go back to that one first so that this video makes more sense. Okay, so internal resistance. There's an equation in your data sheet that says V is equal to E minus IR. And I want to start here because I do think equations help you visualize the physics. So V stands for our potential difference. Our potential difference is the same as it's always been, the way we done it in GCSE. The potential difference is if I have my cell and I was to connect a voltmeter across it, what that potential difference tells me, remember from the last video, we said it was the energy transferred per unit charge between 2 points on a circuit or 2 points in the circuit. E stands for our EMF. And what the EMF stands for is technically it stands for the electromotive force. You don't need to know that, you need to know a definition for it. So an EMF, what it means was if our cell was perfect, how much energy is transferred to each unit charge. So the definition we're going to have for EMF, again, we know the equation E equals VQ. So to find what the voltage or the potential difference is, it's energy per unit charge. And always start with this equation. So what our EMF stands for, it tells us what the energy transferred per unit charge, energy transferred per unit charge from the source or the cell to move the unit charge around the circuit. So remember, what potential difference was the energy transferred per unit charge between 2 points in a circuit. EMF is the energy transferred to that unit charge from the source to move that unit charge the whole way around the circuit. Okay? But we can see if there is current flowing, so if we have a complete circuit and we have current flowing, what's going to happen is the potential difference is going to equal whatever the EMF is, take away I times R. So what we're saying is the potential difference is always going to be less than the EMF, less than our perfect cell, if there's current flowing through our diagram. So what happens is that little r there, it stands for internal resistance. So what you're imagining is I have a little resistor inside the cell with it. It's called the internal resistance. So what it really means is you can think about the cells aren't perfect. When a unit charge or an electron moves through that cell, it's going to lose some energy on traveling through the cell itself. So let's say the EMF was 10 volts. But let's say it's going to lose each unit charge is going to lose 1 joule of energy or 1 volt on going through the cell. It's actually going to come out with 9 volts, or each unit charge is going to come out with 9 joules each. So the reason I'm saying it that way is that the potential difference is 10. If we're looking at a unit charge, that's where we get 10 joules. So if it's 10 volts, we want to think that each unit charge is getting 10 joules of energy. But they're losing 1 joule of energy on going through the cell. So that's why they only come out with 9 joules of energy. So even though the EMF was 10, the potential difference is going to be 9 because we actually lost some energy due to the internal resistance. So that's what it's called. This part here is called the lost PD. So what the lost PD is, the lost potential difference, is the energy lost per unit charge on traveling through the cell due to the internal resistance. And that's what we're representing then by that little r. But remember, don't forget any GCSE rules. If I have a bulb connected here and the potential difference here is 9, remember the potential difference across the components is the same, so the potential difference here is still going to be 9 volts. Okay? So if we look at this question, it says the EMF is 15 volts. They've written that beside my cell. I want to calculate the internal resistance. I would make sure that you draw a little internal resistor beside it so you remember that that cell isn't perfect. There is some lost PD, some lost energy per unit charge on traveling through the cell. So if I put a voltmeter across it, it's always going to give a lower reading than what the EMF is. So it says the potential difference is going to be 10 volts when the switch is closed. The reason it's specified when the switch is closed, and I forgot to put one on my diagram, the reason it's specified when the switch is closed, because when the switch is open, if you look at our equation, V equals E minus IR, when the switch is open, there is no current flowing. So when the switch is open, the current is 0. So the potential difference will equal the EMF. So it's only when the switch is closed and we have current actually flowing through our circuit, that's when the potential difference is less. And it says what potential difference is going to be 10 volts. And we're trying to calculate what the internal resistance is. So write my equation, V equals E minus IR. The potential difference is 10 equals the EMF, which is 15. Take away the current times by the internal resistance. But I don't know what the current is for my circuit. So that's when I go back to my GCSE knowledge. If I wanted to find out what the current through the circuit was, I always use the equation V equals IR. The potential difference across the cell, which was 10, equals the current times by the resistance of the circuit. Okay, so the resistance of my circuit is the two resistors in series with each other, which means the resistance of my circuit is 90. So what I have is 10 is equal to my current multiplied by 90. So find the current, what we do then is divide both sides by 90. So we do 10 divided by 90. So when you do 10 divided by 90, you're going to end up with a current of 0.11 amps. Okay, so again, 40 plus 50 is 90. My potential difference was 10. What we did was 10 divided by 90 to get my current of 0.11 amps. Now I know the current, I can plug it into this equation. So I have now is 10 is equal to 15, take away 0.11 times by the internal resistance. And we know the current is still 0.11 because that current is a series circuit is the same everywhere. So if a current is flowing through my resistors, it's the same current that is flowing through my cell. So I want to figure out what that internal resistance is. So what I would do is subtract 15 from both sides. So I have negative 5 equals negative 0.11 times R. So to find what R is, all we do is divide both sides by negative 0.11. So I do negative 5 divided by negative 0.11 to figure out that my internal resistance of this cell is ridiculously high of 45.45 recurring or 45.5 ohms. So again, a ridiculously high example, but it's just to show you how you plug your numbers in. So again, what we did here was subtract 15 from both sides to get negative 5 is negative 0.11 times by R. We divide both sides by negative 0.11. So 5 divided by 0.11, which gives us the 45.45 recurring or 45.5 ohms. So if you found the video useful, just remember to like and subscribe and share it with your friends and drop me any comments of any other topics you would like me to go over.